Hey everybody, we're going into section 2.4. We're talking about exponential function manipulation. And this is a really great way to think about this because I want you to start thinking about what are equivalents in your mind and how can we manipulate it to be the way we want it to be. This is when we start to really see where math comes in. So here we go. I want you to think back and recall the negative exponent property. So remember when we see a number to a negative exponent, this negative here becomes a 1 over, and the b to the n, or the base number to the exponent, goes in the denominator, okay? Think also about the product property for exponents, where when we have the same base, because that base is really repeated multiplication, we're going to add the sum of the exponents. So for example, because I have 2 to the second times 2 to the third, they're the same base. And now instead of multiplying 2 times 3, we're going to add the 2 plus 3. So this becomes 2 to the fifth, not 2 to the sixth. Okay, if you want to see this, we know 2 squared times 2 to the third happens 5 times. So we know it's 2 to the fifth, not 2 to the sixth. That's a really common, simple mistake that people make. Let's make sure that you're not one of them. So let's talk about what a horizontal translation means in the terms of an exponential function. So remember, horizontal translations means we're doing something to the x values. Remember when we learned this, it was something inside the parentheses. So here, because k is adding into the x value in the parentheses, this is going to be a horizontal shift to the left, now remember, because it's funky town, by k units. Okay, where the b is the constant. So in this case, if I were to say, okay, if you've got b to the x plus k, I can also use the product property of exponents backwards. And I can say, well, if this is a sum of those things, I can say this is like saying b to the x times b to the k. Well, I know b to the x is the exponential function. So if I just move these because it's commutative, then we can say, hey, b to the k times b to the x is here. Well, I know b to the k is some number, is like saying, hey, that's our starting value. That's a times b to the x. So what we're saying here really is this horizontal translation is now multiplying vertically, which is a vertical dilation, which is a stretch or a compression. So we're saying these can be equivalent to each other, that when I horizontally translate an exponential function, that's the same as a vertical dilation. So let's see how that can be. So talking about horizontal translations, every horizontal translation of an exponential function written like this, b to the x plus k, is equivalent to a vertical dilation, that's a stretch or a compression, and that's because mathematically we know that b to the x times b to the k can be broken down like this, where we have b to the x is here, and this b to the k is really a constant in front, where it's like we're saying that's now a vertical stretch or compression instead. So let's see what this can look like in an actual function here. So we can see here, hey, if this function is 2 to the x here, and then, so we see this here as well. I'm going to make this a little bit smaller. So this is our 2 to the x exponent here. But if I shift this, whoops. If I shift this to the left, it's a horizontal shift to the left by 3. We see that it shifts right here, right? Everything's shifting to the left. That's this right here instead. We also see that if I distributed, or I took apart that 2 to the x times 2 to the third, well, I know 2 to the third is really 8. And so that's like saying, hey, it's also like saying I'm multiplying by 8, aka a vertical stretch by a factor of 8. And so we see here that this point here at 1, if I multiply it by 8, it's now here at 8. And we can see that we're also vertically stretching it. So we can see that they're the same graph. Okay, so let's go ahead and look at this. So I want you to keep in mind, let f of x equals 3 to the x power. Okay, so then now we're going to let g of x be the transformation of f. So let's see. So g of x, the transformation is 3x times the 9 here. So we're going to describe it in terms of what's actually happening. Well, if the original function was 3 to the x, is there a way that we can write the 9 in terms of a power of 3? Well, I can write this as 3 squared. So 3 squared times 3 to the x is an equivalent. We can also now use the the product property in reverse. We can say this is 3 to the x plus 2. And so now we can say, hey, this is really a horizontal shift left 2 units because remember, it's still funky town. Okay, so if we're looking at this one, so now again, I want you to think mathematically, how can we manipulate this? If I see here that 3 to the x is my original function f, what's happening here? Well, g of x is dividing it by 27. Well, I could rewrite this as 1/27 times that 3 to the x. Well, let's see if we can figure out a way to write that 1/27 as a power of 3. Well, I know that this is like saying 1 over 3 to the third. And if I use that negative exponent property, this is like saying 3 to the negative 3. These are all the same. So if I keep these as equivalent expressions, 3 to the negative 3 times 3 to the x, this is also like saying the same base, 3 to the x minus 3, which tells me, hey, this is actually the same as a horizontal shift. Now, instead of going to the left 3, we're going to the right 3 because it's funky town. All right, looking at the next one, go ahead and push pause and try this one on your own. All right, let's see what we got. So hopefully you got the same thing as me. So again, remember, instead of f of x, remember, what did they say f of x was? F of x is just 3x, but let's just keep that in mind. But that's like saying, hey, divided by 9 is like saying 1/9 times f of x. Well, I remember that f of x is just 3 to the x. So my goal is I want to write this as a power of some sort of 3. So I know 1/9 can be written as 1 over 3 squared. And because I can use the negative exponent rule, I know that this is x, or 3 to the negative 2 times 3x. And now if I use that product property backwards, I know this is like saying 3 to the x minus 2, which now this tells me that this is a horizontal shift to the right by 2 units. Okay, hopefully you got that right. All right, so let's remember something else. Now we're going to recall the power property. So if I'm multiplying b to some exponent by another exponent, so we're saying repeated multiplication to another repeated multiplication. So we're saying, like, let's say a base 2 to the 2 all to the third power. What we're really saying here is we're going to multiply those exponents. So this is like saying b to the m times n, which in this case would be 2 to the 2 times 3, which would be 2 to the 6th. So remember, power property means that a power to a power is really multiplying those exponents, okay? So if I'm looking at that, how does that change its graph? Well, we know that it changes its graph because it's repeated multiplication. Okay, so if I'm repeatedly multiplying this, this means that we're going to either be compressing or stretching this. This is another way of saying dilation. Okay, so another way to see this here is when I see some base number to a power of c times x, I can change this and I know, hey, this is actually we can use that power property backwards. This is b to the c all to the x power. Well, now this looks like an exponential function, but now instead of b being the base, b to the c is the new base. So now we've got a new base value. of b to the c, whatever that is. And this is going to give us a horizontal dilation. So let's talk about that a little bit more. So we know every horizontal dilation of an exponential function written like this, b to the cx, is equivalent to a change of the base, which we just saw, of an exponential function, where b to the c to the x power and b to the c is a constant, and c cannot equal 0. So let's see how that actually plays itself out. So here I see if I've got 2 to the x power, well, I know, like, let's say x was 3. So here's 1, 2, 3. If I follow this up, this is about 8 here. Well, I can say, hey, I know that if I were to do a horizontal dilation, okay, a horizontal, that means multiplying by 3. This is, remember, it's funky town. So this is actually a horizontal compression by 1/3, okay? So if you can imagine, I'm squeezing this original 2 to the x, and I'm squeezing it horizontally so that it's 1/3 that horizontal space. Well, I can say that this is the same thing. If I simply change that base, that instead of 2 to the 3 times x, this is like saying 2 to the 3rd to the x power. Well, 2 to the 3rd is really just 8. So that 8 is now actually going to be a vertical stretch, right? And we can see that here, that instead of being at this point 1, 1, it's now at the point 1, 8. So we can see that it's now vertically stretching upwards as well. So let's talk about this. So if f of x is the exponential function 3 to the x power, let's let g be the transformation of that function f. So remember, if g of x is a transformation, we need to think about how can I get 9 to the x back into the terms of 3 to the x. So how can I make this 9 into a 3? Well, I know 3 squared is the same as 9, and that x is still there. So this is really like saying, hey, this is really 3 to the 2x. This is the same as a horizontal compression or shrink or dilation by not 2, because remember, funky town, and so it's 1/2, okay? Or you could say that this is a horizontal dilation by 1/2. Let's look at the next one. So again, f of x, remember, is 3 to the x. So if I raise it by a power of 1/3, that's like saying 3 to the negative 3x. So there's two things happening here. So remember, this is inside the parentheses. This is a horizontal compression or dilation, and it's the opposite of multiplying by 3. So it's a dividing by 3 or multiplying by 1/3, compression by 1/3, but it's also got this negative here, and that negative means that it's a flip, and it's flipping horizontally, so it's over the y-axis. You can also call that flip a reflection. Okay, lastly, let's talk about the kth root of b. So this is another kind of something that you're going to recall from before. If I have b to the 1/k, this is called the kth root of b. So if I look at this b to the 1/k, I like writing it like this a little bit better, that this denominator now becomes the index of the root of that b. And we call this the kth root of b. We also see here this 1 is actually an invisible 1 right here. So whatever is in that numerator is your power on whatever's inside that index, okay? Where k has to be a natural number because we can't have decimals in an index of a root. So a natural number, remember, is like the numbers that you counted in kindergarten, preschool, 1, 2, 3, and so on. They can't be 0, they can't be negative, they can't be parts. Okay? Last couple things we're going to try. So let's evaluate these functions. Remember, anytime you see evaluate h of 1, anytime I see x, I'm going to replace it with 1. So here we go, 2 times 5 to the 1/2. that's like saying 2 times 5 to the 1 over 2. Well, this fraction now becomes, I know the index is 2, and this is 5 to the 1. So we got 2 and times the root of 5. Okay, last one. Let's evaluate it at -2. So h of -2 is 6 times 2 to the -2 over 3. So let's do this. 6 times, remember that negative now becomes a 1 over. What's left is 2 to the 2/3. This 2 to the 2/3 is now going to become a 3 in the index. And what's left inside is that 2 to the 2. Let's clean this up a little bit. We've got 6 times 1 is just 6. And in the denominator, we have that third root. 2 to the 2 is 4. We're going to let this be the way it is. Don't worry about rationalizing right now. The only time that you would need to rationalize this, if you saw this on the exam, there was a multiple choice and it didn't have your answer, you could then rationalize it to see if it was the same. But for now, we don't need to rationalize it. This is perfectly fine. All right, that's it for today. We'll see you next class.